Hi, everyone. Today I want to talk with you guys about significant digits. Significant digits are really important. They're pretty darn significant, if you will, when used in science and measurement and things like that. So, a lot of things that we're going to go over about measurements and how we know how precise a measurement is. So, let's get into our notes for this subject. Uh, if you have the PowerPoint and you want to follow along, you can absolutely do that. Or if I'm getting too far ahead of you, feel free to pause the video at any time and catch up to get where we're at here. So we're going to go through our notes and learn a little bit about significant figures and why they're important as well as what they are. So significant figures, okay, are used to determine how precise a measurement is. Okay, how precise a measurement. And when we learn about precision, which we'll have another slide on accuracy and precision, right? Precision is how close a data point or a measurement is to the actual value, okay? So we use significant digits as well to indicate how precise that is. So a measurement that includes all of the known digits in that measurement plus one estimated digit. So whenever we have a measuring instrument, say a ruler or a yardstick, or meter stick, I should say, we will measure to the smallest point that we can read on the meter stick. Then we will estimate one additional digit, okay? So there's a few rules in determining how many significant figures are in a value, okay, in a term or a number that we have. So the first rule is that any number that's a non-zero is going to be significant, right? Zero alone, sometimes it's not that important, especially if it's all by itself, but definitely any number that is not zero is always going to be significant. Our second rule is that if we have two significant digits, two non-zeros, and then we have zeros in between those significant digits, those zeros that are in between those significant digits are also significant, okay? Leading zeros, right, numbers that might start with a zero are not significant, but any zeros that are between digits that we've already determined to be significant, those zeros are also going to be significant, okay? Our third rule for significant digits is all final zeros that are to the right of the decimal and, okay, it has to meet both of these, to the right of the decimal and to the right of non-zeros, those zeros are significant. We'll do some examples on this to kind of help us through this third rule. And then our last rule, rule number 4, all zeros that act as placeholders are not significant. Okay, there's an exception though. Okay, zeros are significant if they're between non-zeros or at the end of non-zeros if there is a decimal point. Okay, so if they're to the right of that decimal point. Again, we're going to do some examples here. So, all right. If you have access to the PowerPoint here, there's a little video kind of sum up these rules for you as well. And I think there's a couple of examples on there also. We're going to go through a couple here right now. So our first example under rule number 1, okay, if I have the number 120, okay, I have a 0 at the end. That 0 after the 1 and 2 is not significant. Okay, it acts as a placeholder at that point, and we don't have it to the right of a decimal. So there's only 2 significant digits. Our next example, the number 2000, those zeros again act as placeholders, right? We don't know how precise a tool someone was using to measure that 2000, whatever they were measuring, right? It's possible they estimated, right? They could have said there could actually be 2,300, but the tool or whatever they were using to measure that was not precise enough. So they end up estimating it to be about 2,000. So one significant figure in the number 2,000. Okay. So now we have rule number 2, right? Zeros in between significant digits are also going to be significant. So if I look at the number 102, now that 0 is significant because the 1 is significant, the 2 is significant, and so therefore the 0 that's between them is also significant. So in that number, we have 3 significant digits. Okay, our next example for that is 3050. Now we have zeros in 2 places here. We have one zero that's between 2 significant digits, okay, because the 2 non-zeros are always significant. So that first 0 is going to be significant because it's between those. Now this last 0 is not significant. And the reason it's not significant is because it acts as a placeholder. It is not between 2 significant digits, okay, and it is not to the right of the decimal point. All right, here we get to rule 3. We had our example in rule 2 of 102. Well, this is also 102. However, we have a decimal point and we have the 0 to the right of the decimal point. So we have a significant digit to the left of the 0. We also have a decimal point to the left of the 0. That makes this 0 significant. And what that tells us in science and measurement is that tells us that someone measured this to a tenth of whatever they were measuring, a tenth of a meter or a tenth of a centimeter, okay? And sometimes that might have been estimated, and we'll get into that here a little bit later also, but remember that last value after the significant digit is going to be estimated. So, but this is still going to be significant. That tells us how precise that measurement is. So in this example, there are 4 significant digits, okay? Same within this example, right? We have 1 and 4 1,000ths. So even though we don't have a measurement or any non-zeros here, these non-zeros are to the right of the 4 and to the right of the decimal point. That makes these 2 zeros significant, again, telling us how precise our measurement was. These 2 zeros obviously are going to be significant because they're in between 2 significant digits, the 1 and the 4. So for that value, we have 6 significant digits, okay, even though we have those 2 zeros on the end. Remember, if it's to the right of a significant figure and to the right of a decimal point, those zeros are significant. All right, and our last rule, okay, we have 0.0045, okay? These zeros in front of the 4, even though they're to the right of the decimal, they're not to the right of any significant digits. Therefore, those zeros are not going to be significant. So only the 4 and the 5 are our significant digits in this value, okay? So 2 significant figures. In our last example, okay, I moved one of those zeros over for you, kind of give you an example, right? If we have the 2 zeros in front of the 4, again, those are placeholders, and we'll get into scientific notation here in a minute and talk a little bit about that. But the 0 that's after the 5, right, is to the right of a significant digit, and it's to the right of the decimal place, making it significant, and so that value has 3 significant digits. All right, so most of you probably already know about rounding. There are 3 rules in regard to rounding. 2 of them I'm going to hold you to, the other one not so much for the scope of this class. However, I do want to go over them briefly. So first rounding rule, you want to determine what your last significant figure is, okay? Then you go to the right of that figure. If that value is less than 5, you do not round up the significant digit. Again, we'll have some examples here. Okay, the second rounding rule is if that digit to the right of the last significant figure is more than or equal to 5, then we round up the last significant digit. Okay, again, I'm not going to go through the last rounding rule. You can write it down if you'd like, but I'm not going to hold you to that one. So some examples here for rounding rule number 1. If I have 124 and I'm rounding that to 2 significant digits, the second significant digit is the 2. So I want to look one place to the right of that, which is 4, and round it. So if it's less than 5, I drop it, okay? And replace it with a 0, right? So my answer is going to be 120 there. In our second example, I have 12 and 41/100ths. Okay, I want to round that to 3 significant digits. So I'm going to look at the third significant digit, which is a 4, again. And then I'm going to look at the number that's to the right of that and round it either up or down. In this case, it's below 5, so I'm going to drop that 1. I don't need to put a 0 here, right, because this takes place to the right of the decimal point, okay? Up top here, if I remove this 0, I would end up with just 12, right, instead of 120. Okay, I think we can agree that's a lot more accurate there. Here, I can just drop the 1. I don't want to add a 0 because if I added a 0, how many significant figures would there be? Right, there would be 4 significant digits, and I can only round this to 3 significant digits. Therefore, we drop the 0. All right, rounding rule number 2, 275, if I wanted to round that to 2 significant figures, okay, if I look at the second significant figure, which is 7, and then move 1 place to the right, which is 5. If it's a 5 or higher, I round it up. In this case, we round that up, which means we carry the 1, right? We'll round that up to a 10. Okay, carry the 1, we end up with 280. Okay, as we round that up, we'll round up that 7. Again, 280 is 2 significant digits, and we're to the left of the decimal place, so we need to have that 0 there. In this example, okay, 0.03798, we want to round this to 3 significant digits. Now, this is where things can get a little tricky, and this is where I see a lot of students make some mistakes. So if I look at the third significant digit, these first zeros are placeholders. So number 9 here is our third significant digit. So I want to look 1 place to the right of that at the 8, and that tells me I want to round it up. So if I round it up, this 9 has to get rounded up to a 10, but I have to carry the 1. So what we get is 0.0380. Okay, I can't just drop the 0 and say 0.038 because that would only be 2 significant digits. I have to keep the 0. That also tells us that this measurement was precise to the 10,000ths place instead of just to the thousandths place. Okay, so that's why that place is important, and that's why those significant digits are important, is because they tell us how precise our measurement is. They tell us how good our equipment is in our measurement, things like that. Okay. All right, let's take a look at scientific notation here for a minute. Scientific notation, okay, you may already know, is set up to make very, very large numbers or very small numbers not be so large appearing, right? It makes it a little bit easier for us to write those numbers, right? If I wanted to, I don't always want to write out, 200 billion with all the zeros, okay? Sometimes I might like to write that in scientific notation with just 2.0 times 10 to whatever exponent I would need for that, okay? So here's how this is set up. So we have 3 numbers, typically between 1 and 10, okay, depending on how many significant digits we need, followed by times 10 to an exponent. Okay, that time 10 to the exponent tells us how many times we needed to move the decimal place. So the exponent can be determined by the number of decimal places we move, okay, in order to move that either to the left or the right, depending on whether the exponent is positive or negative. Okay, if exponents are negative, we move the decimal to the left. If exponents are positive, we move the decimal to the right. Now, another way that I like to think about this is if I look at a number and it has a negative exponent, that tells me that after moving the decimal, I should have a number that's smaller than that coefficient that I'm looking at. And we'll look at the parts of that here in a minute. So it's actually smaller. So that tells me I need to move the decimal to the left because that's going to make the number smaller. If the exponent is positive, that tells me that I should end up with a number that's larger than that coefficient that I'm looking at. And so I should move the decimal to the right as it's going to make the number larger. So here's those parts of a number in scientific notation. We have our 1.23, which is our coefficient. Okay, that's our coefficient. Then we have our base, which is 10, okay, and our exponent. So 10 to the 4th, okay, times 1.23. So as I mentioned here, this exponent is positive. So I'm going to want my end number, if I were to move the decimal place, okay, I want this number, 1.23, to be larger. So if I move that decimal to the right, that's going to make the number larger. Okay, so I would end up with 12,300 in this case. Okay, if it's negative, I'm going to move it to the left. So the thing you need to know with regards to significant figures are that the only digits you will count as significant digits in a number in scientific notation is the coefficient. Okay, this base and exponent are just placeholders. Okay, we do not count them in our figure for the amount of significant digits. So how many significant figures are in this example? Okay, 3. Okay, just the number of terms there in that coefficient, 1.23. There are 3 numbers there. All right, and they are all significant. The other thing to remember is you should always have one number to the left. You should have one number that's also a non-zero to the left of the decimal. So all of these values in the coefficient will always be significant, assuming you wrote it properly in scientific notation. All right, so at some point we're going to have to do some calculations, right? Especially in physics, okay? We have lots of calculations, and it's going to be important to know how many significant figures we need in our calculations and how many we should end up with in our answer. So a few rules, okay? Something I like to do is make sure that I keep one extra significant figure during the calculations. By having that extra one, that eliminates some rounding errors and some different things like that, and allows me to then drop however many digits I need to at the end of the calculation, and then keep the proper number of significant figures. Okay, and the second thing is you'll round after all the calculations have been made, right? As I mentioned, after you were done with the calculations, we want to have an answer with the proper number of significant digits, because that tells us how precise our measurements were. All right, even if we have some measurements that are more precise than others, I'll tell you about how this takes that into account here. So in those calculations, addition and subtraction rules differ from multiplication and division rules. With addition and subtraction, okay, we round to the least precise measurement. All right, so if I had the number 12, all right, that's going to be less precise than if I had something that was measured 12.41. Okay, so that limits the amount of significant figures we can keep in our calculation. We'll do some examples on this as well. In multiplication and division, okay, whichever number in that calculation has the least number of significant digits, your answer can only have that number of significant digits. Let's get to some examples here. So an addition and subtraction example, I have 17.45 plus 34 plus 27 6/10. So what's my answer going to be? Well, there's a couple things that you want to look at first. Okay, which term is the least precise? All right, if we look at this, the 34 only measures to the ones place, whatever tool we were using to make that measurement. 27.6 was measuring to the tenths place, and 17.45 was measuring to the 100th place. Okay, that's going to be our most precise, right? Because we were able to measure to a much smaller, finer detail there. 34 is going to be our least precise. So our final answer can only be to the ones place. Okay, and again, this is just for addition and subtraction, right? That's our least precise. We can only go to the ones place. So if our answer, okay, is going to be 80. Now, you might have punched this into your calculator, and I hope you did, because the answer you probably got in your calculator was not 80. All right, but we then have to round to those two significant digits, or to the ones place. Sorry, to the ones place. Okay. All right, in multiplication and division, let's do an example here. I have 3.45 times 0.3 times 24. So we need to look at how many significant digits we have in each term. So we have 3.45, all right? All these are non-zeros, so all of those are significant. So we have 3 significant digits in our first term. 0.3, okay, the 0 is just a placeholder. 3 is the only non-zero we have that's significant, and therefore we only have one significant digit in that term. 24 has 2 non-zeros, and so we have 2 significant digits. So what's our answer going to be? Okay, well, which term had the least number of significant digits? Right, it was 0.3. So since 0.3 had the least number of significant digits at 1, our answer can only have one significant digit. So 0.3, only one significant digit. So as our answer, if you punch this in, you probably got 24.84. Well, that answer would be incorrect. The reason it would be incorrect is because it has 4 significant digits, and we don't even have one single term that has 4 significant digits. We can't say by answering 24.84 that all of our measurements were that precise, because they weren't. All right, instead, we have to round to one significant digit. So our first significant digit is a 2, right? Then we're going to look one digit to the right and see if it's a 5 or higher, or if it's lower than 5, and round accordingly. In this case, the correct answer for this problem would be 20. Okay, 20 has only one significant digit. All right, so those can be a little bit tricky. I hope that helped you, and we'll have some practice problems that you guys can work through for these. So one last thing that I want to go over is the difference between accuracy and precision. And you also have a worksheet on accuracy and precision that you'll be doing here. And this is where you'll want to get some of the definitions for those two things. So accuracy describes how near a measurement is to the standard or true value. All right. So a lot of times there's an accepted value, something that we know, like for instance, aluminum should have a density of 2.7 grams per centimeter cubed. All right. If we did an experiment to determine the density of aluminum, right, and we didn't get 2.7, right, how accurate is that? How close were we to that accepted value? Precision, okay, is the degree to which several measurements are close to each other. So it doesn't necessarily mean that it's close to the accepted value, right? But did we take a measurement? Was that measurement repeatable? Did we get something similar each time that we did that? All right, so we'll go over that a little bit more in class next time we meet. All right, so now you have some practice problems and some things to work on your own. So let me know if you have any questions. Shoot me a message, anything like that. I hope this video has been helpful to you guys, and I will see you in the next one. Thanks.